Welcome to night cosmos sleep. At the center of a galaxy nearly 300 million light-years away, an unusual point of light appeared. Visible and ultraviolet light began changing first. Nearly a month later, X-rays from the region close to the black hole repeated a similar pattern. It was the same event, yet the two signals did not emerge at the same time. This raised a very clear question. Why did the X-rays come later? X-rays are usually produced in hot gas close to a black hole. If light from the inner region had traveled outward and caused more distant gas to glow, then the X-rays should have changed first. But the data showed the opposite. Visible and ultraviolet light appeared earlier, while the X-rays changed only afterward. This delay was not caused by X-rays traveling more slowly. X-rays, ultraviolet light, and visible light all move through a vacuum at the same speed. The delay must therefore have been created at the place where the star was torn apart. The two signals left the galaxy at different times, then crossed nearly 300 million years of space before reaching Earth. The time gap between them remained unchanged. The event is known as ASA 14 Li. It occurred when a star passed too close to the black hole at the center of its galaxy. Uneven gravitational forces stretched the star out of shape and transformed it into long streams of matter. Some of that material moved away, some returned, and some continued deeper into the region near the black hole. Scientists could not see this entire process clearly. From such a great distance, the event appeared only as a tiny point of light. They could not watch individual streams of gas curve around the black hole or follow a single fragment of matter. What they had instead were changes in brightness, the order in which the signals appeared, and traces of material carried within the light. From those measurements, a path gradually began to emerge. The visible and ultraviolet light may have been produced farther out, where streams of matter collided with one another. A disturbance in the gas then continued inward. Only when it reached the hotter region near the black hole did the X-rays begin to change in the same rhythm. The delay between the two signals therefore acted like a clock. It revealed how long the disturbance took to travel from the outer region into deeper space. By studying the order of the light, scientists could reconstruct the path of the material even though they could not see its shape directly. The star involved in ASA 14 Li disappeared long ago. Yet the silence between those two signals still preserves a trace of its final journey. To understand why the second signal arrived late, we must first understand how a star can remain near a black hole for a long time, only to lose its shape completely after passing too close just once. To understand why the star in ASA 14 Li could be torn apart, we first need to let go of a very familiar image. A black hole is not a giant vacuum cleaner pulling everything around it inward. If that were true, stars near the centers of galaxies could not remain stable for millions or billions of years, yet in reality, most of them continue moving along their orbits, much like planets circling the Sunday. At a sufficient distance, the gravity of a black hole is no different in principle from the gravity of any other object with the same mass. A star can orbit a black hole without falling into it, as long as its speed and trajectory are appropriate. Its sideways motion is what keeps it from plunging straight down. The star is constantly falling toward the center, but at the same time, it is continuously moving to the side, creating a curved path around the black hole. This is also how Earth remains in orbit around the Sunday. The Sun is always pulling Earth toward itself, but Earth does not fall into the solar surface because it is moving sideways fast enough. An orbit forms through the balance between gravity pulling inward and motion carrying an object forward. Near a black hole, the same principle still applies. A star is therefore not in danger simply because it belongs to the same galaxy as a black hole. It may even pass through a relatively nearby region many times, while keeping its shape intact. The real danger begins only when its orbit carries it too close into a region where gravity no longer acts almost equally across the star's entire body. A star is an enormous object. The side facing the black hole is always slightly closer than the side facing away. At large distances, that difference is too small to produce any noticeable effect. But as the star moves deeper into the strong gravitational region, the near side is pulled significantly harder than the far side. This imbalance begins stretching the star in one direction while compressing it in another. This is what is commonly known as a tidal force. On Earth, the tidal pull of the moon helps cause ocean levels to rise and fall. Near a black hole, the same principle can become powerful enough to overcome the star's own gravity, which normally holds its layers of matter together. The star can no longer maintain its familiar round shape. Its outer gases begin to peel away, first from the side nearest the black hole, and then progressively across the entire structure. But for a star to enter such a dangerous region, its orbit must first change. A star moving along a stable path does not normally leave that path on its own and suddenly plunge toward a black hole. The answer may lie in the environment at the center of the galaxy itself. It is a crowded place. Many stars move along different orbits, sometimes passing relatively close to one another. They do not need to collide directly for their gravity to alter one another's motion. A single small interaction may make little difference. Over many encounters, however, a star's orbit can gradually be disturbed. In some cases, the star may lose some of its momentum and begin following a longer, narrower orbit. It still circles the center of the galaxy, but each passage carries it closer to the black hole. In other cases, one strong interaction with another star or stellar system may push it onto a new path almost immediately. We do not know exactly what placed the star in Assassin 1/4 Lie on its final orbit. No telescope had been following it before the event began. Astronomers saw only the consequences after the star had already entered the dangerous region. But no unusual or mysterious cause is required. In the crowded environment around a galactic center, the occasional star being pushed onto an orbit that passes too close is a natural result of many gravitational interactions unfolding over time. Among countless stars, continuing along ordinary paths, only one needs to enter a curve narrow enough for the entire story to change. From the outside, the black hole may still appear almost silent. It produces no light of its own, and without much matter falling toward it, the surrounding region may not become hot enough to shine brightly. This is why many black holes at the centers of galaxies are so difficult to detect. They can contain enormous mass and still remain hidden in darkness, because there is no steady supply of matter producing light around them. Scientists often have to infer their presence by observing the motion of nearby stars and gas. But when a star passes too close, that silence is temporarily broken. Matter is pulled away from the star, collides, heats up, and begins to glow. A region that was once nearly invisible suddenly becomes clear across several kinds of light. The black hole itself does not shine, but the material moving around it can create a flare bright enough to be seen from an immense distance. In that sense, the star is not only destroyed, it also briefly reveals a black hole that had been hidden at the center of its galaxy. Its streams of gas become tracers that allow us to measure the motion, temperature, and structure of a region of space that would normally be almost impossible to see. Assassin 1/4 Li appeared during exactly such a moment. Before then, the black hole at the center of its galaxy may have existed quietly for a very long time. Then a star entered an orbit that brought it too close. The gravitational pull across its two sides became increasingly uneven. Its round shape slowly stretched, the first layers of gas were stripped away, and the region surrounding the black hole began to shine. Among millions of stars still moving around the galactic center, only one entered a path that was too narrow. But distance was not the only factor that determined its fate. The size of the black hole itself also mattered. A larger black hole does not necessarily produce a more visible disruption. In some cases, the star may pass beyond the event horizon before light from its destruction has time to escape. In the case of Assassin 1/4 Lie, the star came close enough to be torn apart, yet it was still outside the region from which light could no longer return. That narrow balance is what allowed us to see what happened. To understand why, we need to imagine two invisible boundaries around a black hole, with the star's fate depending on which one it encounters first. The first boundary is not a physical surface. It is the distance at which gravity begins acting so differently across the two sides of the star that the star can no longer hold itself together. The side facing the black hole is pulled more strongly than the side farther away. Once that difference exceeds the star's own gravity, which keeps its matter bound together, the outer layers of gas begin to separate. The star stretches out and gradually becomes a stream of material. The second boundary is the event horizon. This, too, is not a wall or a solid surface. It is the limit beyond which no signal can return to the outside universe. Light emitted from within that boundary cannot reach us. Whatever happens there, telescopes cannot observe it directly. What matters is not only how powerful the black hole is, but also where these two boundaries lie in relation to one another. If the star is disrupted while it is still outside the event horizon, the hot gas and light produced during the process have a chance to escape. Some of that light may travel across space and eventually be detected by telescopes on Earth. But if the star crosses the event horizon before it is fully pulled apart, most of the disruption remains hidden. From the outside, the star may simply fade and disappear, leaving behind little or no obvious flare. This is one of the ways black holes differ from many familiar objects. When we think of something with greater mass, we often imagine that it must produce a stronger and more visible effect. But for a star passing close to a black hole, that is not always true. The larger the black hole, the wider its event horizon becomes. Beyond a certain point, the boundary of no return may lie outside the region where a sun-like star would begin to be torn apart. In that case, the star may cross the event horizon while still remaining relatively intact. It is still subjected to enormous gravitational forces, but light from the later stages of its destruction can no longer escape. A larger black hole does not necessarily create a brighter stream of gas. Instead, it may hide nearly the entire event. This does not mean that every massive black hole causes stars to disappear in exactly the same way. The outcome also depends on the size and structure of the star, the path it follows, and the rotation of the black hole. A large star with an extended outer envelope may begin to come apart farther away than a smaller, denser star. A rapidly spinning black hole can also shift the positions of important boundaries. But for this story, we only need to keep one simple principle in mind. The event becomes clearly visible only when the star is disrupted before crossing the point of no return. The black hole involved in ASASSN 14 Li has a mass several million times that of the Sunday. That is enormous compared with any individual star, but it still falls within a range where a star can be torn apart outside the event horizon. The black hole was powerful enough to create a tremendous difference in gravity across the star, yet its event horizon was not so wide that it concealed the entire process. The star therefore entered a very particular region. It had come too close to survive as it once had, but not so deep that every trace of its destruction was hidden from the outside universe. Its layers of gas began to separate where light could still escape. The material was stretched, heated, and set into motion around the black hole. Those processes created the point of light that telescopes detected from nearly 300 million light-years away. We can imagine this as a very narrow opening. Farther out, the gravitational pull is not strong enough to destroy the star. Farther in, the event horizon prevents all information from returning. Only in the space between these two regions can a star be torn apart while still allowing the light from its destruction to escape. ASASN 14 Li passed through exactly that opening. If the star's orbit had been slightly wider, it might have only swept past and continued on its way, perhaps mildly distorted, but still intact. If the black hole had been much larger, or if the star had traveled deeper, the entire process might have vanished behind the event horizon before producing a clear signal. But in this case, distance, mass, and trajectory combined in a way that made the event observable. What we saw was not the black hole itself. The black hole remained dark. The flare came from the star's material as it was pulled away, collided, and heated outside the event horizon. In other words, the light did not allow us to look inside the black hole. It only allowed us to follow what happened just before the final boundary. This is also why stellar disruption events are so valuable. They allow scientists to probe a region of space that would otherwise produce almost no light. For a brief time, the star's material traces the motion around the black hole. It reveals where the gas is stretched, where streams of matter meet one another begin receiving different amounts of energy and following different orbits. Some material is pulled deeper toward the black hole, some continues outward. The rest stretches between those two directions, forming a stream of gas far larger than the original star. From that moment on, there is no longer a single star moving around the black hole. There are only countless fragments of matter beginning separate journeys of their own. A larger black hole, then, does not always produce a brighter disruption. For us to observe the event, the star must pass close enough to lose its structure, while the destruction must still occur where light has a path outward. ASASSN 14 Li existed within exactly that fragile balance. The star was torn apart outside the event horizon, and light from its material began spreading into space. But after that moment, the different parts of the star did not all fall in the same direction. Some were captured by the black hole. Some gained energy and continued farther away. Others would return, curve around the black hole, and eventually collide with the very stream of material they had once belonged to. After the star in ASASSN 14 Li was torn apart outside the event horizon, it did not immediately disappear into the black hole. This is a point that is very easy to misunderstand. When we hear that a star has passed too close to a black hole, we often imagine the entire star being pulled straight inward in a single moment. But the reality is far more complex. Once the star lost its shape, its material began moving in many different directions. Some continued toward the black hole, some traveled outward before returning, and some may have escaped the region entirely. To begin with, this event was nothing like a supernova explosion. In a supernova, changes deep inside a star cause it to release an enormous amount of energy and throw matter outward in every direction. In a tidal disruption event, the star does not explode from its core. It is pulled apart from the outside by differences in gravitational force. The side of the star, closer to the black hole, was pulled more strongly than the side farther away. Once that difference became too great, the star's own gravity could no longer hold all of its layers together. Its round shape began to disappear. The star was stretched along the direction of its motion while being compressed in other directions. Layers of gas that had once rotated and moved together as a single body began to separate. There was no single instant when the entire star suddenly dissolved into one complete stream of gas. The process unfolded continuously. As the star swept through the region closest to the black hole, the outer layers were easier to pull away and separated first. Material deeper inside resisted for longer, but eventually it too was affected as the tidal force exceeded the star's ability to hold itself together. During that brief interval, different parts of the star no longer received the same amount of energy. The side closer to the black hole moved deeper into the gravitational field, while the far side experienced a weaker pull. Once the star was no longer a single body, even a small difference in position could place its material on very different orbits. Some matter lost orbital energy and remained bound to the black hole. It did not necessarily fall straight inward at once. Instead, it followed long, curved paths, moving around the black hole before gradually returning. Other parts gained energy as the star was stretched apart. They could continue outward, escape the black hole's gravitational hold, and drift into the space surrounding the galactic center. Between those two outcomes was a great deal of material carrying many different amounts of energy. Some was held very tightly. Some remained only weakly bound. Some lay close to the boundary between returning and escaping. The star should not be imagined as splitting cleanly into two halves. In reality, it became a long stream of matter, with every section carrying its own speed, position, and fate. The fraction of material that falls inward or escapes is not the same in every event. It depends on the mass, size, and internal structure of the star, as well as the path it follows past the black hole. If the star is only partially disrupted, its core may even survive and continue moving. If the disruption is complete, most of the original structure disappears. But even then, the black hole does not capture all of the material immediately. At this point, the idea of a separate, intact star is no longer useful. Before the encounter, every atom belonged to a single structure held together by shared gravity. Afterward, those atoms were drawn into a ribbon of gas far longer than the star's original diameter. The front of the stream may already have passed the black hole, while the trailing end is still approaching. Different sections of the same stream can become separated by enormous distances. You might imagine a drop of ink being stretched into a long trail through flowing water. At first, the color is concentrated in one place. As the current draws it out, different portions begin to separate. Some move faster, some more slowly, and some curve with the flow. Around a black hole, however, this motion does not unfold in a calm stream of water. It takes place within a powerful gravitational field, where every portion of matter follows its own orbit. Now, let us choose a single carbon atom that once existed inside the star and use it as our viewpoint for this journey. It was not an atom that telescopes could follow directly. Among the enormous amount of material in the star, there is no way to identify one individual atom from Earth. But tracing its imagined path can help us understand more clearly what happened after the star lost its shape. Before the disruption, this carbon atom rested within a stable layer of the star. It moved together with the atoms around it, held within the shared structure by the star's gravity. Nothing suggested that it was about to leave the place that had contained it for so long. As the star approached the black hole, everything began to change. The carbon atom and the surrounding gas were pulled away from their former position. The distances between it and the atoms that had once been nearby began to grow. The shared motion of the star was replaced by the motion of a stream of gas being drawn out across space. In this story, the carbon atom belongs to the portion of matter that remained bound to the black hole. After passing through the closest region, it did not fall straight inward. It continued outward along an elongated orbit. For a time, it appeared to be moving away from the black hole, but it was not traveling fast enough to escape the gravitational pull completely. As it moved farther away, its outward motion gradually slowed. Like an object thrown upward that steadily loses speed, the stream carrying the carbon atom eventually reached the most distant point of its orbit. Then it began to return. The black hole did not need to chase it or pull it back with some new force. The stream had remained within the black hole's gravitational field all along, and its orbit had been determined from the moment the star was disrupted. But not every part of the material returned at the same time. The portions held more tightly, followed shorter orbits, and came back sooner. Material with more energy traveled farther, and required more time to return. The stream therefore did not come back as a single body. It returned gradually, piece by piece, spread out over time. This had important consequences for the light produced by the event. When the first material returned to the region near the black hole, it began to collide, heat up, and glow. Other portions arrived later. The brightness of the event changed according to how much matter was returning and how the different streams interacted with one another. While the carbon atom was beginning its journey back, another portion of the star continued outward. This material had gained enough energy to escape the black hole's hold. It left the central region along open trajectories, carrying with it matter that had once belonged to the star. Moving away did not mean that it immediately vanished from all observation. The region around the galactic center is not completely empty. It still contains gas, dust, and streams of material produced by other stars. As the escaping debris moved through this environment, it could push against and compress the surrounding gas. Those interactions could create additional signals at other wavelengths, sometimes appearing later than the original flare. Even the material that never returned to the black hole could therefore leave a trace. It carried the story of the disruption outward, beyond the place where the star had been torn apart. By then, one star had become many separate journeys. Some atoms moved deeper toward the black hole. Some traveled outward and later returned. Others escaped the system. Some may have remained within hot streams of gas around the black hole for a time before their final fate was decided. All of these paths existed within the same event. There was no single route leading from the star into the black hole. What happened was more like an immense junction, where the old structure was dismantled, and every portion of matter followed the orbit allowed by its energy. This is also why the light from the event did not come from only one location. Matter was spread across many distances. Some moved into hotter regions closer to the black hole. Each location could produce a different kind of signal. From Earth, we could not see these individual paths directly. The entire system was too small and too distant to appear as separate ribbons of gas. But the way the light changed over time revealed that the material was not all traveling toward the same place. Some signals came from the outer regions. Others appeared closer to the black hole, and still more traces emerged after the main flare had begun to fade. The black hole therefore did not capture the entire star during its first close approach. It destroyed the star's structure, distributed energy among its different parts, and retained some material while allowing other portions to continue outward. The process of absorbing the debris could last far longer than the moment in which the star itself was pulled apart. Among those streams, our carbon atom was now returning. It had once existed within an almost spherical star, then had been drawn into a long ribbon of gas, swept through the region near the black hole, and carried outward. Now it was falling back with the bound portion of the stream, but its return path did not perfectly overlap with the route it had followed before. Near the black hole, space and time altered the orbit in ways that are unfamiliar in everyday life. After curving through the strong gravitational field, the stream returned along a path slightly offset from its earlier one. The difference may have seemed small, but within a long stream of matter moving at tremendous speed, it was enough to create a violent encounter. The returning gas could cut across the section of the stream that was still moving inward. Atoms that had once belonged to the same star, and had once moved together within a stable structure, were now rushing toward one another along two different trajectories, and even a slight shift in their paths was enough for the star, after losing its shape, to meet itself again. The stream of matter carrying the carbon atom is now returning toward the black hole, but it is not following exactly the same path it traveled before. After sweeping through the region of intense gravity, the stream's orbit has rotated slightly. The angle of that shift is very small, but for a long ribbon of fast-moving material, even a slight change is enough for the new path to cross the old one. In more familiar orbits, an object often returns close to its original position after each circuit. Near a black hole, the motion is not so simple. Space around such an enormous mass is curved, preventing the path of the material from closing perfectly. The stream passes its nearest point, travels outward, and then returns along a direction slightly different from the one it followed before. The leading end of the debris stream has already curved around the black hole and begun moving outward. Meanwhile, the trailing portion is still traveling inward. The star has been stretched into such a long stream that its different parts cannot complete the journey at the same time. One section is moving away while another is still approaching, and eventually their paths intersect. They once belonged to the same star. Before the disruption, every layer of gas was held within a stable structure and moved around a shared center. Now, each portion carries a different amount of energy, follows a different orbit, and unexpectedly meets the others again in an entirely new state. The encounter is not gentle. The streams of gas are moving at tremendous speeds. When they collide, they are compressed, redirected, and stripped of some of their original ordered motion. The energy does not disappear. It is transformed into heat, into chaotic movement among particles, and eventually into light. The collision region heats up very quickly. Atoms and charged particles continuously transfer energy to one another. The gas becomes denser, more turbulent, and brighter. Visible and ultraviolet light can be produced in this region before the material reaches the deeper areas closer to the black hole. The first source of light does not necessarily lie close to the event horizon. It may appear farther out, where the streams of matter cross their own paths. This detail helps explain why the visible and ultraviolet light from Assassin 1-4 Li changed before the X-rays did. If all of the light had been produced in the same place near the black hole, that sequence would be difficult to understand. But once the collision region is placed farther out and the X-ray emitting region farther in, the progression becomes clearer. The gas streams meet first, producing visible and ultraviolet light. Then some of the material continues deeper inward. The carbon atom in our story also enters this collision region. Before the impact, it had been moving within a stream of gas along a relatively well-defined path. Afterward, that earlier order is almost completely lost. The atom is swept into a hotter region where particles collide continuously, and their directions change again and again. The star has met itself, but the encounter does not reunite the pieces that were torn apart. Instead, it further disrupts their former orbits. The streams of matter mix together, lose some of their energy, and begin following shorter paths around the black hole. Not all of the gas changes in the same way. Some retains much of its energy and continues outward. Some is slowed considerably. Other regions are deflected in different directions. The true structure is far less orderly than two thin, glowing streams crossing at a single point. Illustrations often simplify the scene into two intersecting ribbons of gas because that is easier to follow. In reality, the streams may be broad, twisted, uneven, and colliding in several places. They may also meet more than once before the material gradually settles into a more stable pattern around the black hole. The important point is the loss of energy. Before the collision, some of the gas may have followed a very long orbit, traveling far outward before returning. After converting part of its motion into heat, it no longer has enough energy to maintain such a wide path. Its orbit begins to shrink. The material does not fall straight into the black hole. It still has sideways motion and continues circling the center. But each collision causes it to lose a little more energy. Its path grows shorter, its distance from the black hole gradually decreases, and the gas begins concentrating in a deeper region. From a long, scattered stream, the material slowly shifts toward a denser rotating structure around the black hole. This transformation does not happen in a single moment. Many collisions, repeated changes in direction, and different portions of gas all contribute to the gradual reorganization. Closer to the black hole, the gas is compressed and heated so intensely that it emits X-rays. But the X-ray region does not respond. The instant visible light appears farther out. A change in the flow of matter needs time to travel from the collision site into the deeper region. The two signals do not appear together because they record two different stages of the event. Visible and ultraviolet light reveal that the gas streams have just collided farther out. X-rays reveal that the effects of that collision have reached the hotter region closer to the black hole. Scientists do not directly watch a single cloud of gas travel across that entire distance. The system is too small and too far away to be resolved clearly. From Earth, everything still appears as one point of light. What reveals the direction of motion is not an image, but the order in which the light changes. When the optical and ultraviolet brightness rises or falls, the X-rays later vary in a similar rhythm. That repeated pattern shows that the two regions are connected. The delay between them indicates that the influence is moving from the outer region inward, rather than the other way around. What travels deeper may not be an intact mass of gas. It could be the material itself, or a change in density, speed, or the amount of gas flowing toward the black hole. In either case, the data indicate that the variation begins in the collision region and appears in the X-rays only afterward. Visible light arrives first, not because it travels faster. It arrives first because the place that produces it changes first. The X-rays appear later because the X-ray emitting region responds only after the influence from farther out has moved deep enough inward. That difference in timing allows a system that cannot be seen clearly to reveal its internal structure. The collision region lies farther out. The X-ray region lies closer to the black hole. Between them is matter losing energy and continuing inward. The carbon atom is no longer traveling along the same long orbit as before. After being swept through the collision region, it now belongs to gas that has lost some of its energy. Its path has shortened, carrying it closer to the hot regions surrounding the black hole. The star has lost its shape, but its material is still changing. Streams of gas that once separated across great distances return, collide, heat up, and glow. Some of that matter continues deeper inward, beginning the next stage of the journey. If the first light was produced in an outer collision region, how could scientists know that the material truly moved closer to the black hole? The answer lies in the X-ray signal that appeared almost a month later. At this point, the story of the star can be understood through three main regions. In the first, the star passes too close to the black hole, loses its former structure, and is stretched into a long stream of matter. In the next, different parts of that stream meet again, collide, heat up, and produce visible and ultraviolet light. Deeper inside lies the hot gas near the black hole, where X-rays are emitted. The motion follows the same sequence. The star is disrupted, the gas streams collide farther out, the material continues inward, and only then does the X-ray emitting region near the black hole begin to change. 3 regions and 3 stages, yet from Earth they do not appear as 3 separate images. Everything is compressed into a single tiny point of light, and what allows scientists to separate those regions is not shape, but time. From Earth, the 3 regions we have just described do not appear as 3 separate images. The place where the star was torn apart, the region where the gas streams collided, and the area where the X-rays were produced are all too distant and too close together in the sky for telescopes to resolve individually. Even with extremely powerful instruments, scientists could see only a small source of light near the center of the galaxy. To understand what was happening inside that point of light, they needed another way to observe it. ASASSN 14 Live first appeared as a source of light where nothing like it had been seen before. A region that had once seemed unremarkable suddenly brightened, signaling that something significant had happened around the central black hole. Once the event was recognized, telescopes began monitoring it through repeated observations. The goal was not simply to capture a clearer image, but to watch how the source changed over time. A single image preserves only the state of the event at one particular moment. It can show whether the source is bright or faint, but it cannot reveal how the light increased when it began to fade, or whether one kind of signal changed before another. Motion is not contained in any single image. It appears only when many measurements are placed in sequence. The Swift spacecraft was especially useful for this monitoring because it could observe the source across several different bands of light. For our story, we need to focus on only 3: visible light, ultraviolet light, and X-rays. All 3 are forms of light, but they are often associated with regions of matter that have different temperatures and physical conditions. Visible light is the portion closest to what the human eye can detect. Ultraviolet light carries more energy and is often produced by hotter gas. X-rays are associated with matter at extremely high temperatures, usually deeper within the flow surrounding a black hole. These 3 forms of light should not be thought of as 3 completely separate images. They are more like 3 ways of listening to the same event, each one sensitive to a different part of the system. After every observation, scientists recorded the brightness of the source in each type of light. The measurements collected over time formed curves showing how the brightness changed. These curves were not smooth and regular like perfect waves. The source might gradually fade over a long period, But within that overall decline were smaller variations, a slight brightening, a brief dimming, and then another change appearing later. Those small fluctuations provided the most important clues. The general fading showed that the event as a whole was gradually weakening, but an individual variation could reflect a specific change in the amount of gas, its temperature, or the speed at which material was moving around the black hole. When the same pattern appeared in more than one kind of light, the possibility that the signals were connected became especially significant. Researchers placed the visible light record beside the ultraviolet record. The two curves showed many similar changes. When one brightened or dimmed, the other often changed in nearly the same way. This close relationship suggested that the two forms of light might come from the same region, or from regions responding almost simultaneously. The X-ray record told a different story. It also contained variations with familiar shapes, but those variations did not occur at exactly the same time. A change that appeared first in visible and ultraviolet light seemed to be repeated in the X-rays only later. This discovery did not come from looking at a single point of light and guessing what might be happening inside it. It emerged only after many observations were combined. Long-term trends were separated from shorter variations, and the timing of the different forms of light was compared carefully. It was much like hearing an echo in a large room. What matters is not only whether the sound is similar, but also when it arrives, because that delay reveals something about the path it has taken. In Assassin 1-4 the X-rays were not simply changing in a completely independent way. Part of their rhythm seemed to follow what had already happened in visible and ultraviolet light. At first, it might seem that the X-rays arrived later because they had farther to travel, or because that kind of light moves more slowly. But light does not behave that way. X-rays, ultraviolet light, and visible light all travel through a vacuum at the same speed. They differ in wavelength and energy, not in how quickly they move through empty space. The distance from the galaxy containing ASASSN 1-4 to Earth was nearly the same for every photon emitted from that region. The small separation between the outer and inner zones was far too insignificant compared with a journey of hundreds of millions of light-years to explain the observed delay. The X-rays did not take nearly an extra month simply because they began from a deeper region near the black hole. The source of the delay had to lie within the event itself. The two signals did not leave the galaxy at the same time. Visible and ultraviolet light were produced first. The X-rays carrying the same pattern appeared only after the X-ray emitting region had time to respond. Two letters sent from the same city may arrive several days apart, even if they travel along the same route and take the same amount of time in transit. The reason is not the speed of the delivery, but the dates on which they were sent. The second letter arrives later because it left later. The same was true of the two signals around the black hole. Once emitted, both traveled at the speed of light. The time gap between them already existed before their journey to Earth began. Each photon carried the moment when it left its source. An ultraviolet photon might have begun its journey just as the streams of gas collided in the outer region. An X-ray photon departed later, after the effects of that change had reached the hotter gas closer to the black hole. They traveled through space for an almost unimaginable length of time, yet the order in which they left remained unchanged. In this way, timing data became a kind of map. An ordinary map uses position to show which place lies before or beyond another. Here, the telescopes could not see clearly enough to measure the distance between the regions directly. Instead, the order in which the signals appeared revealed the direction in which the change was moving. Visible and ultraviolet light changed first, placing their source near the beginning of the sequence. The X-rays changed later, showing that the hotter region near the black hole responded afterward. Between those two regions, some process must have carried the change inward. What was moving inward may not have been a single, clearly bounded cloud of gas. The flow of matter around the black hole was too hot, too broad, and too turbulent to be divided into neat packages like train cars. The change may have traveled as a denser region of gas, a stronger inward flow of material, or a disturbance in speed and density. The telescopes could not identify individual particles. They could only record how the light responded as the state of the gas changed. This is also why the idea of mapping must be understood carefully. Scientists did not create a sharp image showing the outline of every gas stream. Instead, they determined the relative order of the emitting regions. The optical and ultraviolet region changed first. The X-ray region changed later. The time between them became a clue to the connection between the two. Had Assassin 14 Ili been observed only once, the entire story would have disappeared. Scientists might have known that the source was bright, but not whether it had just brightened or was already fading. There would have been no way to recognize that the X-rays were following a variation that had occurred earlier. Only through repeated observations over a long period did an underlying order gradually begin to emerge. This method appears throughout astronomy. Human beings can rarely approach the objects they study, nor can they watch distant processes from every possible angle. Instead, light is collected over time, and each small change is used to infer motion in places far beyond our reach. In the case of ASASSN 14 Li, patience in observation was just as important as the sensitivity of the telescope. Each measurement contributed only a very small piece. On its own, it revealed almost nothing about the path of the material. But when many data points were joined into a sequence, patterns of variation began to appear. And when sequences from different kinds of light were placed side by side, a new connection emerged. From a point of light too small to resolve, scientists began to identify at least two distinct regions. The first was associated with visible and ultraviolet light. The second produced X-rays closer to the black hole. These regions were not behaving independently because variations that appeared in the outer region were repeated in the inner one after a delay. The carbon atom we have been following still lies within the turbulent gas left behind by the collision. From Earth, no one could identify it, much less point to a location and say that it was there. But if the layer of gas containing it became denser, hotter, or moved inward more rapidly, the light from the entire region could change. When that influence reached the X-ray emitting area, a corresponding signal appeared in the data. The path of an individual atom was not being recorded. Instead, the collective motion of the gas stream left a much larger trace, one strong enough for telescopes to detect. Through those traces, the journey from the outer collision region to the hotter inner region was no longer completely invisible. The delay between the signals was not an unwanted part of the data that needed to be removed. It was the most important piece of information. If every variation had appeared at the same time, it would have been difficult to determine which region was influencing the other. If the X-rays had changed first, the story would have pointed outward. Energy from near the black hole might have been causing more distant gas to glow. But the observed sequence began with visible and ultraviolet light. The direction of the story therefore pointed inward. The change appeared first in the outer region, and only later became visible in the X-rays. The material disturbed by the collision did more than heat up and glow where it was. Part of its influence continued moving toward the black hole. The light records took the place of a camera that could never exist. There were no images of gas streams circling the black hole, and no frames capturing the carbon atom as it moved from one region to another. There were only curves, rising and falling in brightness, repeated variations, and the intervals of time between them. Yet sometimes a time series can be more useful than a photograph. A photograph shows where something is. Time reveals what happened first, what followed, and in which direction two events may be connected. When the records of ASASSN 14 Li were placed side by side, they revealed more than light coming from different regions. They also suggested the direction in which the change was traveling, beginning where the gas streams collided, then moving inward toward the hot region near the black hole. What remained was the precise clock for that journey. How long was the delay? And what could it truly reveal about the motion of the material? The answer lay in the 32 days separating the two pulses of light. 32 days separated the two patterns of light in ASASSN. 1,4 Li. Visible and ultraviolet light changed first. The X-rays repeated a similar pattern afterward. That interval is not long compared with the lifetime of a star, but it was enough to change how scientists understood the entire event. The brightness of the X-rays had already revealed the presence of extremely hot gas around the black hole. Yet the intensity of the light was not the most important clue. The order in which the signals appeared was what revealed the direction of motion. The signal that came first showed where the chain of changes began. The signal that followed showed which region responded later. Before the observations of ASASN, 1,4 Li were compared side by side, a familiar explanation still seemed reasonable. X-rays could have been produced in the hot gas close to the black hole and then traveled outward. More distant layers of gas might have absorbed that energy and re-emitted it as visible and ultraviolet light. This kind of process occurs in many astronomical systems where high-energy radiation from an inner region causes surrounding material to glow. If Assassin 1,4 Li had worked mainly in that way, the X-rays should have changed first. The inner region would have produced the initial signal. That light would then have taken a short time to travel outward, heat the more distant gas, and cause it to shine again. The observational record should have begun with the X-rays, followed by visible and ultraviolet light. But the data curves appeared in the opposite order. Light from the outer region changed first. The X-rays responded about 32 days later. An explanation based on X-rays illuminating material farther out could no longer account for that sequence. The direction of the story had to be reversed. The variation began in the outer region and then moved inward toward deeper areas. Streams of matter that had once belonged to the same star collided at a relatively large distance from the black hole. The gas was compressed, heated, and began emitting visible and ultraviolet light. The collision also changed the motion of the material. Some of the gas lost energy, could no longer maintain its long orbit, and began moving deeper into the gravitational field. That change did not appear in the X-rays immediately. The X-ray emitting region lay closer to the black hole, where the gas was much hotter. Only when matter, or a disturbance within the flow, reached that region did the X-ray brightness begin to follow the pattern that had appeared earlier farther out. 32 days became a clock connecting two regions of space. This clock did not measure distance in the same way as a ruler. The time could not simply be multiplied by the speed of light, because whatever was traveling inward was not necessarily a freely moving photon. It may have been gas itself, a denser region within the flow, a change in the speed of the material, or an increase in the amount of matter moving toward the black hole. By combining the delay with models of how the gas moved, scientists could determine the relative arrangement of the two sources of light. The region producing visible and ultraviolet light lay farther out. The X-ray region lay deeper inside. Between them was a path that matter, or a change within that matter, required time to cross. The map of ASASSN 1,4 Li had no clear outlines, colors, or visible ribbons of gas. It was created through sequence. The outer light appeared first. The inner light appeared later. The interval between those moments became the trace of a journey that could not be observed directly. Telescopes did not see an individual cloud of gas leave the collision region and gradually approach the black hole. There was no tiny point of light that could be marked and followed from beginning to end. From nearly 300 million light-years away, the entire region remained compressed into a very small source. What appeared in the data was the collective response of an enormous amount of matter. It would therefore be too simple to say that the same cloud of gas was observed twice. Scientists could say more confidently that the two emitting regions were connected. Variations that began in visible and ultraviolet light were repeated in the X-rays after a relatively consistent delay. The most likely direction of that connection was from the outer region inward. That caution is important. The flow of matter around a black hole is not a river with clearly defined banks. The gas is stretched, collides, twists, and mixes together. Its density varies from one place to another. A denser region may move inward, but it may also create pressure or alter the amount of gas flowing ahead of it. Timing data cannot preserve every small detail, yet it can still reveal the overall direction of the motion. The 32-day delay also answered part of the question raised at the beginning of the video. Why did the lower energy light appear before the X-rays? The reason had nothing to do with the speed of propagation. Visible light did not travel faster, nor did ultraviolet light follow a shorter path to Earth. They were produced earlier in a region farther from the black hole. The X-rays were created later, after the effects of the collision had reached the hotter gas farther inside. Once they left their sources, all of the photons began their long journey through space at the same speed. The time separating them had already been established before they left the galaxy. An ultraviolet photon escapes from the collision region. It leaves just as the streams of matter have met, while the gas is being compressed and the first light is spreading outward. The photon does not know what will happen behind it. It simply continues across the space between galaxies. While the ultraviolet photon is already on its way, the matter around the black hole continues to change. Some of the gas loses energy and moves deeper inward. The flow becomes denser in certain places and thinner in others. Motion that had once been spread across long orbits begins to concentrate closer to the center. Nearly a month later, the hot X-ray emitting gas responds. An X-ray photon leaves from a deeper region. It begins its journey later than the ultraviolet photon, but both travel through space at the same speed. Nearly 300 million years pass as they make their way toward Earth. Galaxies move, stars are born, and disappear. Yet the order of the two photons remains unchanged. The ultraviolet photon arrives first. The X-ray photon follows. The 32-day interval remains exactly as it was when they left their sources. When telescopes detect those two signals, humanity receives more than light from a distant place. It receives a fragment of time preserved throughout a journey of nearly 300 million years. The interval between the signals carries the rhythm of matter moving around a black hole long ago. A photograph usually tells us where something is. The delay in ASASSN 14Li reveals the direction in which a change traveled. It began where the streams of matter collided, then moved toward the hot gas closer to the black hole. Through timing alone, scientists were able to distinguish the outer and inner regions of a system they could not resolve clearly. This is why the late arrival of the X-rays mattered more than their brightness alone. A powerful X-ray source tells us that matter near the black hole is extremely hot, but delayed X-rays reveal a connection between different regions, showing that the outer source of light was not merely receiving energy from within, but may instead have been where the change began. That direction of motion also helps explain how a disrupted star gradually becomes a flow of gas circling a black hole. After losing its structure, the material does not immediately form a stable ring. The long streams must meet, collide, and lose energy. Only then can gas from the collision region begin moving onto smaller orbits. The 32-day delay records one part of that transition. It lies between the moment the debris glows farther out and the moment the inner X-ray region responds. It does not capture the entire process from an intact star to gas crossing the event horizon, but it preserves one segment clearly enough for us to recognize the direction of travel. The carbon atom we have been following may lie within the gas moving deeper inward. After the collision, it no longer follows the long orbit it once did. Its energy has been redistributed through countless interactions. The stream carrying it gradually approaches a region of higher temperature. No one can see that atom, nor does anyone know exactly where it is at every moment. But the collective motion of the surrounding gas changes the light. When the outer region brightens first, and the X-ray region responds later, the shared journey of the material is revealed through two signals separated by 32 days. In astronomy, the empty interval between two signals can sometimes seem like little more than a period of waiting. Here, that interval is the evidence. If the signals had appeared at the same time, the relative positions of the regions would have been more difficult to determine. If the X-rays had arrived first, the influence might have been moving from the inside outward. It was the delayed appearance of the X-rays that revealed the opposite path. 32 days is not a period during which light somehow slowed down, nor is it a random error in the observations. It is the rhythm left behind by the system as the change traveled from the place where the gas streams collided to the hotter region nearer the black hole. From a tiny point of light, a map gradually takes shape. Farther out lies the place where the stream of matter meets itself again. Deeper inside is the hot gas that emits X-rays. Connecting the two is a journey lasting nearly a month, recorded not through an image, but through the order of the light. The X-rays have brought us to the region closest to the black hole that telescopes can probe through this event. The gas there moves rapidly, is compressed intensely, and reaches extremely high temperatures. It is easy to imagine that from this point onward, all matter has only one possible path, crossing the event horizon. But the story changes direction once again. Even after reaching deep into the hot region, not every part of the star continues falling into the black hole. Some of the material may still be driven back outward. X-rays bring us to the deepest observable region around the black hole. There, the material no longer drifts in long streams as it did when the star was first torn apart. The gas has passed through many collisions, lost some of its energy, and settled into smaller orbits. The closer it moves toward the center, the faster it travels, the more tightly it is compressed, and the hotter it becomes. Particles within the flow collide constantly, raising the temperature until the region begins emitting X-rays. That light does not come from inside the black hole. The event horizon is not a surface that matter strikes before bursting into light. It is a boundary beyond which no light can return to the outside universe. Every X-ray photon that reaches a telescope must have been produced before the material crossed that boundary. What we see is the final stage of the journey that can still leave a signal behind. The gas has moved very deep, but it has not yet disappeared. It circles the black hole at tremendous speed, hot enough to glow at high energies. Some of it continues losing energy and moving inward. Some remains in orbit. Yet even in this place, where every motion might seem destined to lead toward the black hole, matter can still be driven back outward. A large amount of gas from the star is being concentrated into a small region over a relatively short period. The space around the black hole becomes crowded with hot, rapidly moving matter that is constantly colliding. Heat and pressure rise within the gas. Energy released as the material moves deeper into the gravitational field also contributes to the increasingly intense environment. The black hole continues pulling matter inward through gravity, but not every portion of gas follows a straight and quiet path. The flows interact with one another. The hot inner region can exert pressure on the material farther out. Radiation from the dense area can also transfer momentum to the gas. Some matter is lifted away from its former orbit and blown out of the region near the black hole as hot winds. Inflow and outflow can exist at the same time. Matter approaching the black hole supplies energy to the hot region. That energy, in turn, helps drive some of the gas in the opposite direction. There is no contradiction between these two motions. They simply show that the region around a black hole is not a simple funnel through which everything quietly slides in the same direction. In ASASSN 14 Li, the X-ray observations carried signs of gas moving away from the central region. The true speed and shape of the flow did not appear as a cloud with a clearly defined outline. Scientists recognized the motion through the way the material absorbed light. Gas lying between the X-ray source and the telescope left subtle features in the spectrum. The positions of those features shifted depending on whether the gas was moving toward us or away from us. From those changes, scientists determined that some of the matter around the black hole was moving outward. This was not the original gas that escaped from the star during its first close approach. It was material that had traveled deep into the hot region, joined the flow around the black hole, and was only then driven back out. The carbon atom we have been following may also face several possible paths here. After the collision farther out, it belonged to gas that had lost energy and moved closer to the black hole. Around it, the temperature rose while the motion became faster and more chaotic. If it continued losing energy, the atom could travel with the flow across the event horizon. From that moment onward, every trace of it would disappear from external observation. But it could also lie within a layer of gas being lifted out of the hot region. Collisions, pressure, and radiation from farther inside transfer energy to the surrounding material. If the stream carrying the carbon atom receives enough energy, it changes direction and begins moving away from the black hole. Moving outward does not necessarily mean escaping the entire system. The black hole still exerts a powerful gravitational influence across a vast region of space. Some gas flows may travel fast enough to continue far away. Slower portions may gradually lose speed, reach a certain distance, and then return. Other material may mix with the gas and dust already present around the center of the galaxy. The boundary between escaping and returning is not the same for every part of the flow. Each particle carries a different amount of energy. One atom may be pushed onto a wider orbit while remaining gravitationally bound. Another, after receiving only a little more energy, may leave the region close to the black hole and continue drifting outward. The star was once a single, unified body. Its layers moved around the same center, shared the same gravitational bond, and maintained an almost spherical shape. After its passage near the black hole, that unity was gone. The material divided into many streams from the moment the star lost its structure, then separated further through the collisions that followed. The portion that escaped during the initial disruption moved along open paths into the space around the galaxy. The bound material returned and collided with itself. Some gas traveled deeper inward, heated up, and emitted X-rays. Within that hot region, part of the material was blown back out. The rest continued orbiting, continued losing energy, or eventually crossed the event horizon. There is no single moment when we can say that the star completely disappeared. Its former shape was lost early, but its material continued to exist in many different places. Some had traveled far from the black hole. Some still orbited close to the center. Some was driven outward after first moving deep inside, and some could no longer send any signal back. Seen from Earth, all of these fates are compressed into the light of one very small point. One telescope detects X-rays from the hot gas. Another instrument detects radio waves when outward moving material collides with the surrounding environment. Spectra preserve signs of gas in motion. Each type of signal reveals only one part, but when placed together, the event appears as a network of movement rather than a simple inward fall. Saying that a black hole swallows a star can make the story easier to remember, but it also removes its most complex features. The black hole does not receive the entire star at once. Before any portion of the material crosses the event horizon, the star has already been stretched, dispersed, collided with itself, emitted light, and formed streams moving in many directions. Even the region closest to the black hole does not contain only inward motion. The hot flow acts like a place of constant energy exchange. Material from farther out adds mass and motion. Collisions transform some of that motion into heat. Radiation and pressure transfer energy into other layers. As a result, some portions continue falling inward while others are lifted and blown outward. These winds also affect the environment surrounding the black hole. They carry heat, energy, and elements that once existed inside the star. As the gas spreads, it may encounter nearby material, heating it or pushing it into new positions. The death of a star therefore leaves more than light near the black hole. It may also alter a much larger region around the center of the galaxy. However, we should not imagine a steady wind blowing evenly in every direction. The gas around the black hole may be distributed unevenly. Some areas are denser, while others are thinner. The outflow may be divided into separate regions, change over time, and interact with matter that is still moving inward. Its true shape is far more complex than a spherical shell of gas expanding around the center. The observations allow scientists to confirm that outward motion exists. The details of each flow, where it begins, and what ultimately happens to it still have to be inferred through models. That caution does not make the story less clear. Instead, it preserves the boundary between what telescopes have recorded and what scientists reconstruct using physics. The carbon atom continues its journey. If it lies within the outward moving gas, it may leave the X-ray emitting region and enter a cooler environment. The temperature around it gradually falls as the flow expands. Particles that once collided constantly begin to spread farther apart. Behind it, the intense light from the central region slowly fades. It may never return to the place that was once the star. That place no longer exists. The atoms that once surrounded it have now scattered onto entirely different orbits. Some have crossed the event horizon. Some are still circling within the hot gas. Some are traveling far away with the material thrown outward during the initial disruption. Others are drifting within the newly formed wind near the black hole. All of them once belonged to the same stellar body. After the event, the distances between them may extend from the region just outside the event horizon to far more distant areas around the galactic center. The star's ending does not unfold in one place, nor does it happen in only one way. The matter that crosses the event horizon can no longer add light to the story outside. The material that remains beyond it continues to leave signals behind. Hot gas emits X-rays. Outflowing material absorbs some of that light. Debris traveling farther away collides with the surrounding environment. Each trace appears at a different time and in a different form of light. The 32-day delay revealed that the change moved from the outer collision region into the inner X-ray region. The outflowing gas shows that the journey did not end there. Some material reached the deeper region and then turned back outward, adding another direction of motion to the map of the event. From a single star, many paths now remain. One crosses the event horizon. Another circles the black hole within the hot gas. Another is redirected outward. Still another moved away during the first close encounter. No single path represents the complete fate of the star. This dispersal also leaves one final gift for astronomers. Matter that has not disappeared continues to emit or absorb light. Elements that once existed deep within the star leave their own distinct fingerprints in the spectrum. Nitrogen, carbon, and other elements reveal more than where the gas is or how it is moving. They also carry information about where that material was formed and transformed before the star approached the black hole. The star no longer has a shape that can be observed directly. No image can show exactly how large it once was or how its internal layers were arranged. But the atoms that remain still preserve part of that history. After the light has revealed the path of the material, its chemical composition can help answer the final question: what kind of star was it before it was torn apart? After the star was torn apart, its former shape no longer remained for us to observe. No image had captured it before it approached the black hole. Telescopes detected the event only after the streams of matter had already begun to glow. To learn how large the star once was, how it had evolved, and where the observed material had originally been located inside it, scientists had to search for answers within the remains themselves. Atoms that had not crossed the event horizon continued interacting with light. Some emitted photons as the gas heated up. Others absorbed light at specific energy levels as it passed through them. Each element responded in its own way, leaving a distinctive signature in the spectrum. A spectrum is not an image of the star. It is light separated into many different energy levels. Across that band of light appear narrow lines, like marks in an identification code. The position of each line reveals which element is present. Its strength offers clues about the relative amount of that material, the temperature, and the physical state of the gas. Hydrogen leaves one set of signatures. Carbon has its own. Nitrogen, oxygen, iron, and many other elements also produce characteristic patterns. Astronomers do not need to collect a particle directly from a distant galaxy. Light passing through the gas carries that information all the way to Earth. In ASASSN 14 Li, carbon and nitrogen became two especially important clues. They did more than confirm that the gas around the black hole had once belonged to a star. The ratio between them also preserved traces of reactions that had taken place deep inside the star before it was destroyed. Carbon and nitrogen participate in cycles of nuclear reactions within the cores of stars that are hot enough. Over time, their relative abundances change. Matter that has been processed inside a star will not contain the same elemental ratios as ordinary gas that had already existed around the black hole, or as outer stellar layers that had never reached regions of intense nuclear activity. The light from ASASSN 14 Li showed an unusually strong abundance of nitrogen compared with carbon. That chemical pattern was difficult to explain if the observed material was merely ordinary gas that had been present around the black hole before the event. It was more consistent with matter that had once existed inside a star, where nuclear reactions had altered its original composition. The star had disappeared, but its internal history remained within the atoms pulled away from it. Carbon and nitrogen became two pieces of an old record. From the way they appeared in the spectrum, scientists began working backward to reconstruct the structure and evolution of an object that no longer existed. Early observations had led the star in ASASSN 14 Li to be described rather simply as a star, somewhat similar to the Sunday. That description was reasonable. While the available data focused mainly on brightness, the timing of the variations, and the amount of material required to produce the event. No one had seen the star before it was disrupted, so every early description depended on the model that best matched the information then available. Later, chemical analysis opened another possibility. The nitrogen-to-carbon ratio suggested that the star may have been significantly more massive than the Sunday. A more massive star would reach higher internal temperatures and process its material differently. The layers of gas stripped away by the black hole, therefore, carried signatures consistent with an evolutionary history different from the one first imagined. These two descriptions do not necessarily cancel each other out, with one being entirely correct and the other entirely wrong. Science often begins with a broad estimate and gradually narrows it as more data become available. Brightness reveals one part of the story. The motion of the gas adds another. Chemical composition provides further information about what happened before the event began. A star does not come with a label showing its mass for a telescope to read. Once the object has been torn apart, every conclusion must pass through several layers of inference. Scientists compare the observed elemental ratios with different models of stellar evolution. They search for the type of star most capable of producing the measured amounts of nitrogen and carbon. The result is a range of likely values, not an absolute number that can never change. The process resembles a kind of archaeology carried out in reverse. In archaeology on Earth, researchers find fragments of pottery, layers of ash, or traces of a structure, and use them to infer the community that once lived there. In ASASSN 14 Li, there was no longer an intact star to examine. Only hot gas, scattered streams of matter, and light that had crossed space remained. From those remnants, the earlier story could gradually be reconstructed. Elemental ratios revealed which reactions the material had experienced. Stellar models showed the conditions under which those reactions usually occur. The amount of matter and the duration of the flare helped constrain the star's possible mass. The motion around the black hole revealed which regions the gas had passed through after being stripped away. No one knows the exact order in which every layer of the star was removed, nor is it possible to determine the original depth of every atom that was observed. The chemical signatures allow scientists to conclude only that at least some of the gas carried the composition of material that had once been processed in the star's interior. This clue is especially valuable because the deeper layers of an ordinary star are extremely difficult to observe directly. The light we usually receive comes mainly from the surface. The inner regions are hidden beneath the material above them. When the black hole tore the star apart, the structure that had concealed those deeper layers was also dismantled. Material from inside the star had a chance to appear within the glowing streams of gas. In a sense, the black hole opened the star. It did not do so with a clean cut, but through gravity stretching the layers of matter into long streams. The light from that gas allowed us to detect material that may once have been buried far beneath the stellar surface. The carbon atom we have followed throughout this journey now becomes part of that chemical record. It once existed inside a star, unknown to humanity. After the star's structure collapsed, it may have passed through the collision region, moved closer to the black hole, become swept into the hot gas, or been driven outward again. Whatever its exact fate, that carbon atom and the elements around it helped create the signal collected by telescopes. No instrument could identify that individual atom. Trillions upon trillions of atoms together produced a signature strong enough to appear in the spectrum. The story of each separate particle merged into the larger story of the material. From that collective signal, the origin of the star slowly came into view. Assassin 14Li was not understood through a single kind of observation. Visible and ultraviolet light revealed variations in the region where the gas streams collided. X-rays brought us closer to the hotter region around the black hole. Changes over time connected those regions. Absorption features in the light revealed whether the gas was moving inward or outward. Chemical composition carried the story even farther back, to a time before the star entered its final orbit. A tiny point of light in the sky contains many layers of time. One layer tells of the moment when streams of matter collided. Another records the journey inward toward the X-ray emitting region. Another reveals gas being driven away from the hot inner area. Deepest of all is information that had existed while the star was still intact, preserved in the ratios between its elements. Light tells us more than how brightly a place is shining. It carries information about the temperature of the gas, its speed, its direction of motion, its chemical composition, and the order in which changes occurred. None of this information arrives in words. It is encoded in brightness, wavelength, spectral lines, and the times at which photons reach a telescope. It was the combination of these many layers of evidence that made ASA/SSN 14Li so remarkable. With visible light alone, scientists might have recognized a flare, but struggled to understand how it was connected to the region near the black hole. With only X-rays, the hot gas would have appeared, but the inward journey from farther out would have remained unclear. Without spectroscopy, the origin of the material and the internal history of the star would have been much harder to determine. Each method preserved only part of the event. When those parts were placed together, a consistent story began to emerge. A star passed too close to a black hole. Uneven gravitational forces destroyed its structure. Its matter was divided along many paths. The bound streams returned, collided, and produced light farther out. The effects of that collision traveled inward, causing the X-ray region to change about 32 days later. Near the black hole, some gas continued falling inward while other material was driven back out. The elements that had not disappeared preserved traces of the original star. This reconstruction is still not the final explanation for every stellar disruption event. ASA/SSN 14Li was an especially favorable case to observe. By cosmic standards, it was relatively nearby. It shone clearly across several kinds of light, and it was monitored long enough for small variations to emerge in the data. Another event might look entirely different. Dust within the galaxy could obscure visible and ultraviolet light. The viewing angle might place one emitting region behind a thick layer of matter. A larger or smaller black hole would change the location where the star was disrupted. The type of star, its approach trajectory, and the amount of gas already surrounding the galactic center would also shape the final signal. Some events are powerful in X-rays but faint in visible light. Others shine brightly in the optical range while revealing almost nothing from the X-ray region. Not every disrupted star produces two signals with a connection as recognizable as the one in ASA/SSN 14Li. nor are elemental ratios always clear enough to reconstruct the mass of the original star. For that reason, the model built from this case still needs to be tested against many other events. If similar delays continue to appear, the idea of an outer collision region followed by an inward moving flow will gain further support. If other systems reveal a different sequence, scientists will need to determine which conditions produce each type of signal. Science does not stop when one explanation appears to fit. A successful model must account for the current data and continue to hold up as new observations arrive. Assassin 1.4 provides a clear example, but it cannot fully represent every star, every black hole, or every viewing angle in the universe. That limitation does not diminish the value of what was discovered. From a source whose shape could not be resolved, scientists identified several distinct emitting regions. From a delay of 32 days, they recognized motion traveling from the outside inward. From signatures of gas moving away, they learned that some material was being driven back out. From carbon and nitrogen, they inferred that the original star may have been different from what was first imagined. This examination was not performed on an intact object. There was no surface to measure, no core to observe directly, and no physical sample brought back to a laboratory. Everything was reconstructed from light that had left the galaxy hundreds of millions of years ago. That star was already gone before modern humans appeared on Earth. When the first photons began their journey, our planet was passing through an entirely different age. By the time the light was recorded, the matter around the black hole had probably changed long ago. What the telescopes received was an old record delivered across space. The record is not complete. Many details have been lost. Many steps can only be inferred, and some conclusions may change as better models emerge. Even so, what remains is enough to reveal the broad outline of a star that once existed, produced carbon and nitrogen within its deeper layers, and then entered a gravitational region where its structure could no longer survive. At the beginning of this journey, the question was how two signals that did not appear at the same time could reveal the path of matter. The answer has now expanded far beyond the original delay. Timing established the order of the emitting regions. X-rays showed that the gas had reached a hotter area. Outflowing material revealed that the journey was not moving in only one direction. Spectroscopy carried the story even farther back. Visible light, ultraviolet light, and X-rays were more than 3 kinds of signal. They were 3 parts of a single record. Their changes over time revealed how those parts were connected. Their chemical composition added the history of the material before the record itself began. The star no longer remained intact to be seen. Atoms that had once rested beside one another were scattered across many orbits. Some crossed the event horizon. Some continued circling within the hot gas. Some were blown far away. Others carried chemical signatures and continued interacting with light. The original shape was gone, but not all information disappeared with it. The interval between 2 patterns of light preserved the motion. The spectral lines preserved the composition. Together, they formed a record of an object that no longer existed. As the story reaches its end, we can return to the 2 photons that left the same galaxy at different times. One carried news from the region where the streams of matter met. The other departed later from the hot region near the black hole. Between them lay the time required for the material to continue its journey deeper inward. The star disappeared, but the timing and composition of its light still preserved the path it followed, along with part of the history that had existed inside it long before it ever encountered the black hole. The carbon atom we have been following once existed inside a star unknown to anyone on Earth. For most of its life, it had no journey of its own. It moved with countless other atoms, held within the star's shared structure, passing through hot regions, dense layers of gas, and cycles of change that lasted longer than any human lifetime. The star continued shining in a distant galaxy, unaware that its orbit was gradually carrying it closer to a silent black hole at the center. Then the distance became too small. The side of the star facing the black hole was pulled more strongly than the side behind it. The gravity, that had once held the star together as a sphere could no longer resist that difference. Layers of gas began leaving their former positions, the round shape stretched out, and an object that once had clear boundaries gradually became streams of matter spread around the black hole. The carbon atom no longer remained beside the atoms that had once surrounded it. Portions of gas that had belonged to the same layer were pulled far apart. Some matter gained energy and continued outward. Some remained bound by the black hole's gravity, curved around the closest region, and later returned. The rest stretched between those two directions, neither escaping completely nor moving immediately into the deeper region. From one star, many journeys began at once. The stream carrying the carbon atom may have traveled far outward before gradually slowing. When it returned, it did not follow exactly the same path as before. Near the black hole, its orbit had rotated by a small angle. The returning material crossed another part of the stream that was still moving inward. Atoms that had once traveled together now approached from two different directions. That encounter did not restore the star to its original state. The gas was compressed, its motion became chaotic, and some of the stream's energy was converted into heat. The collision region began glowing in visible and ultraviolet light. This was the first signal in the sequence of traces that humanity would later detect. After the collision, some of the gas no longer had enough energy to remain on its long orbit. Its path began to shrink. The material moved closer to the black hole, traveled faster, became more tightly compressed, and experienced more frequent collisions. The temperature rose until the inner gas began emitting X-rays. Yet even very close to the black hole, the material still did not face only one possible fate. Some continued losing energy and crossed the event horizon. From that moment on, no light from it could return. Some remained in orbit within the hot gas. Other material gained energy through collisions, pressure, and radiation around the black hole, then was driven outward in hot winds. The star did not disappear at a single point, nor did it end in a single moment. Its former shape was lost fairly early, but its matter continued to exist along many different orbits. Some had traveled far from the galactic center. Some still circled close to the black hole. Some had moved deep inward before being pushed back out, and some had crossed the final boundary and could no longer send any signal to the outside universe. The carbon atom in our story could have followed any one of those paths. It may now be drifting within gas moving away from the black hole, remaining inside the hot flow, or already lost beyond the event horizon. No telescope could identify a single atom from nearly 300 million light-years away. Its individual fate cannot be known. Yet carbon did not disappear entirely from the story. Trillions upon trillions of carbon atoms left a signature in the light. They created distinct lines in the spectrum, allowing astronomers to identify the composition of the gas. Nitrogen and other elements left fingerprints of their own. The ratios between those signatures carried a history that began long before the star approached the black hole. The elements in the gas did more than show that the material had once belonged to a star. They also revealed that some of it had undergone reactions within the stellar interior. Carbon and nitrogen did not appear in random proportions. Their distribution reflected the temperature, pressure, and nuclear reactions that had once existed deep within the star. Through those chemical traces, scientists could work backward to reconstruct a star that no longer existed. There was no clear image of it before the event. No one knew exactly how brightly it had shone, what color it would have appeared in the sky of that distant galaxy, or how many stages it had passed through during its life. All that remained was hot gas, scattered streams of matter, and light that had left the region long ago. From the amount of light, its changes over time, and its chemical composition, an approximate picture gradually emerged. The star may have been more massive than first suspected. The observed material may not have come only from outer layers that had undergone little change. Some of it may once have existed deeper inside, where nuclear reactions had altered its chemical composition. This examination took place without anyone touching a single fragment of matter. No gas sample was brought back to a laboratory, and no instrument traveled close to the black hole. The light itself carried the data across the space between galaxies. Each photon preserved a very small part of the story. Its energy revealed the conditions where it was created. Its wavelength offered clues about temperature or the elements involved. Shifts in the spectrum showed whether the gas was moving toward us or away. The time at which the photon arrived helped establish which event occurred first and which came later. A single photon could not reconstruct the entire star. Millions of measurements collected over repeated observations were needed to create patterns of variation clear enough to interpret. When visible light, ultraviolet light, and X-rays were placed side by side, each band added something the others could not provide. Visible and ultraviolet light led scientists to the outer region where streams of gas collided. X-rays revealed the deeper region where matter had become intensely hot near the black hole. Absorption features in the spectrum exposed gas moving outward. Chemical composition carried the story even farther back, to a time when the star was still intact. All of these layers of information were gathered from a point of light too small for its structure to be resolved. Telescopes could not see three separate regions. They could not film the gas streams colliding, capture the material gradually moving into the X-ray region, or follow a wind flowing away from the black hole. There was only light rising and falling, changing in energy, and appearing in a particular sequence. That sequence revealed the most important part of the story. Visible and ultraviolet light changed first. Nearly a month later, the X-rays repeated a similar pattern. If the X-rays had been causing the outer region to brighten, they should have appeared first. Instead, the data pointed in the opposite direction. The variation began where the streams of gas collided. Then matter, or a change within the flow of matter, moved deeper inward. Only when that influence reached the hot gas near the black hole did the X-rays respond. The 32-day delay was not time lost, because light had slowed on its way to Earth. It was the time the system required to move from one stage to the next. Scientists did not convert that number into a distance with a simple calculation. What traveled inward was not necessarily a freely moving photon or a clearly defined cloud of gas. It may have been a denser region, a change in speed, or an increase in the amount of material flowing inward. Although the detailed mechanism remained complex, the order of the signals still revealed the overall direction, from the outside inward. In this way, time took the place of an image. Where telescopes lacked the resolution to separate the structure, the delay allowed scientists to arrange the regions by their relative positions. The optical and ultraviolet region lay farther out. The X-ray region lay deeper inside. Between them was a journey lasting nearly a month. Light revealed not only where something was shining, but also where the change had begun first. Now, let us return to the two photons that opened this entire story. The first photon left the region where the streams of gas collided. It carried ultraviolet energy from a place where the gas had just been compressed and heated. The moment it was emitted, that photon began moving away from the galaxy. It passed through the gas around the galactic center, continued into the space between the stars, and then entered the vast emptiness between galaxies. Behind it, the material had not stopped moving. The gas streams continued losing energy, their orbits grew smaller, and some of the matter traveled deeper toward the black hole. The X-ray emitting region did not change immediately. It responded only when the influence from farther out finally reached it. 32 days later, the second photon left a region of hot gas closer to the black hole. This photon carried more energy and belonged to the X-ray part of the spectrum. It began its journey later, but once it escaped its source, it traveled through the vacuum at exactly the same speed as the ultraviolet photon ahead of it. Both photons crossed nearly 300 million years of space. During that time, other stars were born and disappeared. Galaxies continued to rotate, collide, and change. Earth passed through ages long before human beings appeared. Yet the two photons continued on their way, separated by the interval that had been created near the black hole. Nothing along the journey caused the X-ray photon to move more slowly. No region of space extended its path by an extra month. It arrived later because it had left its source later. When the first photon reached Earth, telescopes recorded the variation in ultraviolet light. Nearly a month afterward, the X-ray photon brought a similar pattern. The time between them remained intact after a journey lasting hundreds of millions of years. That delay was like a fragment of time preserved within the light. It did not retain the entire scene, but it preserved the sequence. It revealed that the outer region changed first, and the inner region responded later. From an interval containing no visible image, the direction of the material's motion gradually emerged. This is what makes light so remarkable in astronomy. When we observe something nearby, we often rely on its shape, color, and directly visible motion. For places far beyond our reach, light must perform many more roles. It becomes an image, a thermometer, a clock, a marker of motion, and a record of chemical composition. In Assassin 1-4, visible and ultraviolet light told the story of gas streams meeting one another. X-rays revealed the hot region close to the black hole. Spectral lines showed whether gas was moving inward or outward. Carbon and nitrogen preserved traces from inside the original star. The 32-day delay connected all of these clues into a single journey. The star had lost its shape long ago, but information about it did not disappear immediately with its former structure. Some of that information remained in the temperature of the gas. Some was carried in the direction of motion. Some was preserved within the elements. Another part endured in the interval between two signals. This evidence does not reveal every detail. We cannot determine the path of each individual atom, nor can we know the exact shape of every gas stream at every moment. Some parts of the story still depend on models and may be revised as new data become available. Even so, the light carried enough information to reconstruct the broad outline. A star entered a dangerous gravitational region. Its structure was destroyed, its material scattered along many paths. The returning portions met in the outer region and began to glow. The change then continued inward toward the X-ray emitting gas. Some of the material was driven back outward. The chemical composition of what remained revealed something about the star before it disappeared. From two signals that did not appear at the same time, scientists found far more than a delay. They discovered a map drawn without visible lines, an examination performed without a physical sample, and a history written into photons that had crossed nearly 300 million years of space. The carbon atom in our story may no longer exist anywhere we can observe. It may have crossed the event horizon, continued orbiting the black hole, or drifted far away within an outflow of gas. But carbon, as part of the disrupted star, still left its signature in the light. The fate of one individual atom was lost, while the trace of an entire star remained. Perhaps this is the quietest part of the story. An object may lose its shape, its pieces may be separated, carried far apart, and never meet again. Yet what happened can still leave an order within the light. That star vanished long ago. The black hole at the center of the galaxy may also have returned to silence after the flow of material gradually thinned. The point of light appeared and then faded. The gas streams continued along paths that humanity could no longer follow clearly. But the two photons arrived. One carried news from the place where the streams of matter met themselves again. The other carried news from the deeper region of hot gas, leaving nearly a month later. The interval between them crossed a span of time longer than the entire history of humanity without being erased. The star has been gone for a very long time. Yet in the silence between those two patterns of light, the universe still preserves the path its matter once traveled.